Hello. Hi, I'm Bob Ippolito, and this is my Drop Acid and Think About Data talk. I'm going to be talking basically just general information that I've learned over the past year or two about the various kinds of databases. There's a lot more out there than just the databases that are typically used for web apps, say Postgres and MySQL. My perspective on this issue is that in 2005, I co-founded a startup called Mochi Media, and basically we have to deal with a lot of data. Our first platform was an analytics platform, basically like a hit counter for Flash content called MochiBot, which collects, as you could imagine, many thousands of requests per second from all these Flash movies all over the world on different websites. And then on top of that, in 2006, we built an ad platform for Flash games. So similar to something like Google AdSense, there's all these Flash games out there with our APIs in it, and we have to serve all those API requests and do all sorts of analytics based on the ads served so that we can decide which ads to show and how to pay game developers and charge advertisers. And we also have a bunch of other cool services that we offer to Flash game developers, such as a leaderboard service that we allow the game developers to just push all of their server-side score stuff to us. And we can integrate that with Facebook, and we can show scores for their friends, and basically take care of all that nasty server-side programming for them, because these guys are really just client-side developers. And they could really use the help of somebody that knows what they're doing on the server side to allow one guy to build a game that gets played by 1 million people a day without having to worry about it. And so our primary business is selling ads, and I thought this was an interesting picture. These are two of our salespeople dressed up to go to GDC this week. So I actually passed up the Game Developers Conference to come here and speak. And so about dropping ACID. ACID is what most databases, relational databases, give you these days. And ACID is like a promise ring that your database system wears. It's an acronym that stands for atomicity, which means that during a transaction, either the whole transaction succeeds or none of it does. Consistency, which is related to atomicity, such that it doesn't explode, right? Like your database is always consistent on disk. If you shut it down or it crashes or something, and you bring it back up, your data is still there. Isolation means that you don't have multiple concurrent writers fighting over things, right? So basically, you can pretend that all of your transactions are happening serially, and everything will just magically be correct. And durability means that your database doesn't lie to you, right? If you do an insert into that database and that transaction succeeds, your database promised that that data is there for you. But the problem with ACID is that it gives you too much. It really trips you up when you're trying to scale a system, particularly across multiple nodes. In typical web services and other kinds of heavy-duty stuff that people are building these days, downtime is really just unacceptable. Right, so to build a system that doesn't have downtime, it first needs to be reliable, and to have a reliable system, you need at least 2 nodes, because the machine could fail. And in order to make a scalable system that can handle lots and lots of writes or reads, you need a lot more nodes than that. And so the problem is that once you try and implement ACID across many machines, the networks make it hard. The algorithms just don't work in a distributed environment at any acceptable speed. So what can you have, right? So a bunch of people much smarter than me decided that you can have 2 of 3 things. You can have consistency, which means your data is correct all the time. You can have availability, which means that you can read your data all the time and write your data all the time. And you can have, or you could have partition tolerance. Partition tolerance means that if you have this big multi-node network, and one or more of those nodes become incommunicado with the rest of the system, that your system can deal with it when those nodes come back online. And you can extend that to expanding your network, like adding nodes, which is also very difficult to implement because you have to then move all the data around. And so another person smarter than me decided that we should come up with a different acronym instead of ACID for these sorts of large systems. And they called that BASE. BASE means that for a web application or a web service, you want it to be basically available, which means that your application works, or at least mostly appears to work almost all the time. Soft state, which means that it doesn't necessarily have to be consistent all the time, and eventually consistent, which means that it will be in some known state, but maybe not right this second. And so the people building applications on top of this kind of methodology is basically everyone that builds big applications. Google, Amazon, Yahoo, Facebook, and I'm sure many of you here are building applications that follow some of these principles. Google's example of a system that follows the principle is Bigtable. So Bigtable manages talking across all these nodes with an algorithm called Paxos, which is a distributed transaction algorithm. It's kind of difficult to describe, but they have a service called Chubby that manages these locks across systems. And Bigtable is interesting because it's actually a single master system where one node knows everything about all the other nodes. Of course, they have this node backed up, and they can bring up another one, and they do a lot of caching of the metadata that node controls. And what they do is they distribute pieces of the database called tablets via their GFS file system, which is a networked file system that they use for basically all of their stuff. And the interesting thing about Bigtable is that it's a hybrid between a row database and a column database, because in a column database you want to store similar things next to each other, and in a row database you want to store like an object and all of its properties for that object in the same place. And so GFS basically does that by taking each of these tablets, which are small chunks of the database, I think about 64 megabytes or something, and they sort it in such a way that all of the columns are right next to each other, which is good for them because what they're able to do once you start putting all these columns, all the similar data, if you put it in the same place, you can make great gains in throughput by using compression. And Bigtable happens to use some proprietary compression algorithms for this. But once you start compressing your data, not only can you store more, but often your bottleneck on databases is I/O. So if you're storing the data in a smaller space, your performance improves because you have to talk to the disks less. And also using a column-ordered storage, you do less disk seeks because even worse than doing I/O is doing random I/O. So they avoid this. And another interesting thing about Bigtable is it's eventually consistent because they basically have an append-only system. They do some garbage collection later, but in order to implement an append-only system, what they do is they tack on a row timestamp for each of these objects. So basically, when you query it, you get several versions, and you just pick the most recent one or the most relevant one. And they also use something cool called Bloom filters, which allows them to have the data distributed across a whole bunch of nodes. And a Bloom filter is basically a little fingerprint, and that fingerprint will tell you that this data might be on this node. But if it says no, then you know the data is definitely not on that node. So you can save yourself from querying all these nodes that definitely do not have the data that you're interested in. And so the good thing about Bigtable is that compression is awesome. It really, really helps performance. And that because they have a single master system, the clients are probably simple. So it's easier for them to write applications that use Bigtable and maintain it and such. And it integrates with MapReduce and Sawzall and all sorts of other proprietary stuff that I don't know that much about. And the bad things about Bigtable is that it's proprietary to Google, and in theory, single master can be a con, but because I'm not privy to that much of the implementation details of Bigtable, I'm not really all that sure. And so a single master system looks kind of like this. You've got the cat in the middle that controls all the metadata, and all the penguins are the nodes that actually contain these tablets. And so Another interesting approach to building a big distributed system is what Amazon built and published in their Dynamo paper. Dynamo is a very sort of basic key-value store data model. It's essentially like a giant distributed Python dictionary. And in order to distribute the data, they use something called consistent hashing. So they have this, they basically come up with a big ring where they have all of their nodes mapped onto that ring. And they have a hash function that picks which node should get that data based on the value of the key. And they have knobs that they can turn that allow the data to be distributed to several nodes for redundancy and also performance reasons. And in order to actually get the data to be consistent across nodes, they use two things. They use vector clocks, which is similar to having a timestamp on every row, except you actually have a timestamp on every row for every node that has written to it. And they have a way of resolving those vector clocks to see which node actually has the latest version. And they do something very interesting called read repair, which means that instead of having all of these storage systems or a single master sort out which node is supposed to have what data at which time, it's actually the clients that talk to this system that fix the data. So what you do when you're a client of Dynamo or a similar key-value store is when you do a read, you read from one or more nodes. And if those nodes disagree about the data, you as the client, it's your responsibility to go right to those nodes and tell them that their data is wrong and put the data in the right state. And the good things about Dynamo is that there's no master, so you're eliminating a point of failure, and it's highly available for write. One of the tenets of the design of Dynamo is that you should always be able to write to it. Even if those writes may potentially fail, you work around that by writing to many nodes at once. You don't consider it completely written until you know that several nodes have been successfully written to. And it's got a bunch of knobs in it so that you can basically change the replication factors. So if you want the database to be really fast to read, you can set your read replication factor to 1, and then you only need to read from one node before you consider it to be consistent. But this can certainly, in a read repair world, this can lower your consistency. But on a per table basis, you know what the right knobs are for that because you know the needs of your application. And the other cool thing about Dynamo is it's relatively simple, and that's why there's a lot of half-baked clones out there of Dynamo. Maybe one of you here has written one. The cons about Dynamo is that Dynamo in particular is proprietary to Amazon, which makes it more or less useless to me. The clients need to be really quite smart. The client that talks to Dynamo has to understand how vector clocks work and has to be able to do all this read repair stuff, and there's other complicated things related to like rebalancing a cluster and figuring out which nodes are a member of that cluster. So there's a way to work around that in that you have routing nodes, which are basically smart clients that you talk to get the data for you. But that introduces an extra hop, which can add some latency that you might not want. Another con is that there's no inherent compression in the system. So that means that you're basically dealing with I/O at the level of the data that you're dealing with. But of course, you can manually have the clients deal in compressed values, but not necessarily compressed keys, depending on how you're using them. And it's not suitable for column-like workloads. So say if you're running a big analytics service, you're not going to be able to do a whole lot with a key-value store because you need to do a lot of aggregate queries. And key-value store like Dynamo is not something that you use to select a bunch of keys that have this prefix or from this certain time and then add it all together. It's just not a system designed for that. It's just a key-value store. And Dynamo looks more like this. Dynamo system is just a bunch of nodes. The nodes don't really talk to each other. They wait for you to talk to them as a client. And it's actually quite simple to implement something like this on the server side, which is why so many people have tried in the past 2 or 3 years. And another really interesting database system is Facebook's Cassandra, which is now an Apache project. It's open source. It's peer-to-peer with no master like Dynamo, but it has a storage model more like Bigtable. And the great thing about Cassandra is that it's open source, so it's actually relevant to people that don't work at Google or Amazon. And it's incrementally scalable, which allows you to, as your data grows, you can add more nodes to this mesh that's storing your Cassandra data. And there's minimal administration, because with an incrementally scalable system, you don't have to plan a whole big migration from one cluster to another. And that is a great thing if you're trying to run a service and also run a lot of a big data store. And the bad thing about Cassandra is that it's not polished yet. They built it for their particular use cases. In particular, the one they talk about the most is inbox searching in Facebook, and that they haven't implemented compression yet, which would actually help considerably, at least for how I want to use it. And this is Cassandra from the game Soul Calibur, which is a game that I like. And so basically my thoughts on all these distributed databases is that distributed databases are kind of like the new framework, except at least in the open source world, none of them are awesome yet. There's no obvious like Django of the key value stores. A lot of people are talking about projects like Project Voldemort from LinkedIn, but what they don't realize is that that's also not finished yet. For example, Project Voldemort, they're working on it, but they don't have it implemented yet. They don't have rebalancing. So if you set up a Voldemort cluster with 10 nodes, and your data grows such that you need 11 nodes, you have to create a new cluster and migrate all your data over, and they haven't implemented any sort of garbage collection to it yet. So if you store something in that database, it never goes away, which increases your need for such a system. And it's just going to be a really interesting space to watch, but there's nothing obvious that I see that should be used right now. But I also think that we don't need another half-baked Dynamo clone. Like, please, if you're interested in working on one of these things, pick one and start submitting some patches. I'm really impressed that Jonathan Ellis, for example, was able to latch on to the Cassandra project, even though it was sort of in an abandoned state from the Facebook team. But through his help and presumably the help of others, it turned into an Apache project and is actually going to be useful in the open source community. And just sort of topic change entirely, away from the distributed stuff. Another thing that a lot of people are using these days in order to augment or replace some of their relational systems are simple key value stores. The advantage of key value stores is that they're super simple and often really, really fast. You can use them basically almost the same as you can use a Python dictionary. So it's a very familiar model to Python programmers. Typically in a key value store, the keys are typically bytes, and the key space is probably limited. Many of the key value stores have some sort of arbitrary, like 1 kilobyte or several hundred byte limit on the keys, like Memcache, for example. And the values are often also just big blobs of bytes, but they often have fewer limits. So you can store, say, a few megabytes or perhaps even more. And the great thing about key value stores is that they're just really, really, really fast and simple. So if you have a sort of model that is conducive to a key value store, it will be fast if you actually use a key value store. And the key value store that's probably most popular right now, although people don't necessarily think of it as such, is Memcached. Memcached is a key value store that people use as a cache. There's no real persistence in Memcached because it's in memory and it's a cache. Everything you want to put in a Memcached instance has to fit in RAM only. And one of the things that makes it useful for some purposes and terribly not useful for others is that it throws data away on purpose. If you store too much data in Memcached, it will start throwing old data away so that you can make room for stuff that you want to be hot on the cache. And it also allows you to program in specific expiration times for stuff in the cache, so that if you don't get your invalidation strategy right, you can still have a somewhat eventually consistent view of your data. And memcached is just lightning fast, and everyone uses it. So it's very well supported. The protocol is super simple. And if you're not using memcached and you've got a system that you're trying to optimize, it's a good first effort to try and put some caching layers on top of that database, so you just don't have to talk to it as much. And my thoughts on caching database results is that caching immutable data is really easy, and you should just do that. And it would be great if your data never changed. But if you're caching mutable data, invalidation just sucks. And if you have an ACID system and you throw in a cache on top of that mutable data, you're probably going to get it wrong, and you're going to have something really difficult to debug. Because putting this cache layer in front, it eliminates several of the ACID properties, depending on how you do it. So just dealing with mutable data in a cache, it becomes really hard. For example, what do you do with a failed transaction, right? So the way that most people are using memcache is that you set the cache as soon as you read it or write it to the database, but what if later on in that transaction the client disconnects and your web framework decides to throw an exception and the transaction never actually succeeds to the database? What happens there? I don't know. Maybe you've got bad cache. And when you have concurrent writers to that cache, it sort of prevents you from getting great isolation, because you're writing to this system that things are reading from without the transaction isolation that ACID gives you. And another thing that often bites us anyway is if you start caching things that are dependent on other cache keys. Say you have a zoo object and an animals object, and when you select the zoo object, you cache the list of animals, and then you delete an animal, and now your zoo object is invalid unless animals know how to delete dependent cache keys from the zoo object. And it just gets really messy. So be very careful if you're developing caches on top of mutable data, or at least understand that you're going to probably lose some of the consistency that your database had otherwise given you. And another cool key value store that I've been working a lot with recently is a project out of Japan that they use to power basically the Japanese version of Facebook. It's called Tokyo Cabinet, and then there's a network server that you can use on top of Tokyo Cabinet called Tokyo Tyrant. Tokyo Cabinet basically has the same use cases as Berkeley DB, which used to ship with Python. The cool things about Tokyo Cabinet is that you get disk persistence, and the manner in which they implement disk persistence, you don't need to have all of the data in RAM all of the time. So you can store data on a single node greater than the amount of RAM that machine has. It's a very performant key value store, at least as far as disk-backed key value stores go. It's actively developed. There's a new version every couple weeks, which could be good or bad, depending on what you're looking for. But typically, the active development is on new features, not bug fixes. Because right now, they're working on adding some sort of hybrid key value store and table store stuff into Tokyo Cabinet. And another cool thing about Tokyo Cabinet is that it has optional compressed pages. So you can get some of the advantages of having compression in your database. And it also, if you're using Tokyo Tyrant, you can implement a similar replication strategy to MySQL, which is useful in many cases, but it makes your whole system bound to the write speed of one node. So it's not great for all replication needs. And another key value store I've been hearing about recently is Redis, which is still very new. The thing about Redis is that they call it a data structure store, not a key value store. And it allows you to do all sorts of cool things. You can match on key spaces. So if you're looking for all keys that start with something or that match some expression, you can do that. And another really useful and interesting thing is that the Redis server allows you to store the values as lists or sets. So you can do list operations and set operations in the process space of the server itself, which is much more efficient than sucking down a value with all of the list contents, manipulating it, and putting it back. And it also allows you to do that atomically, whereas if you fetched it and did the work in the client, it would be much harder to make that operation atomic. But the big downside with Redis is that you have to be able to store your entire data set in RAM, right? Unlike Tokyo Cabinet, it doesn't allow you to push some of that data onto disk and sort of forget about it until you need it again. Redis was designed for very consistent performance, whereas with a system like Tokyo Cabinet, if it falls out of the Tokyo Cabinet's cache, it's going to have to start getting slow going to disk. Whereas Redis just says if it doesn't fit in memory, you can't store it anymore. Although it is disk-backed, so that once you write something to a Redis store, it will be there the next time you start up the Redis store. It's just that it doesn't allow you to store more than you would fit in RAM. And I think that Redis could be used to be a very nice cache server for some purposes. Because of the list operations and the set operations, you should be able to do some interesting things that you can't easily do with Memcache. And another thing that everyone's been talking about recently, even in the ORM talk, is about document databases. Document databases are schema-free, which means that you don't have to deal with creating a table schema and enumerating every single thing you could possibly want. And that makes it really easy if you're actually still developing your application. Because one of the biggest things you run into developing one of these database applications is schema migration. If you want to add a column to something, you often have to lock your whole database or do something really funny with a relational store. But with something like a document database, you simply have some objects that have, or some documents that have the new property and other documents that don't. And you just sort of have to deal with that in the application layer. And it's just great for storing documents because that's what they're built for. CouchDB is basically the document database poster child. It's an Apache project, just like several others. It's got asynchronous replication, but it's the same sort of replication that you get from other systems like MySQL, such that even though you have replication, it doesn't make things faster necessarily because you still have to store all the data on all of the nodes, and that limits you to the write speed of one node. It's JSON-based, which makes it very easy to interoperate with, especially for me because I wrote simple JSON. And an interesting thing about CouchDB is that in order to query it, you basically do that in a sort of map-reduce style by creating what they call views. And you create a view by writing a JavaScript function or a function in a language of your choice that looks over effectively every document in the entire document store and creates a list of the ones that you care about for that view. And you can also mutate the documents a bit while creating the view. And they materialize on demand. So you hit the view once, and then it basically saves that view. And you don't have to generate the view again unless anything in your database changes. And CouchDB has a really neat admin interface. So if you just want to play with a document database, you can boot CouchDB up. It's easy to get started, and it's really fun to play with. But the other document database that I've been hearing a lot about is MongoDB, which I call C++'s revenge. CouchDB is written in Erlang, and MongoDB is written in C++. And one of MongoDB's biggest selling points is that it is just fast. It is significantly faster than CouchDB from the benchmarks that I've read. And MongoDB supports two different data models. Natively, it's got a data model it calls BSON, which is JSON-ish, except it has a binary serialization, and it supports some additional types. Like there's a BSON serialization for regular expressions because that's what they use in their match objects, and it has date-time representations. And it has asynchronous replication just like CouchDB, but they promise auto-sharding soon. They say Q2, but soon is what I'll go with. And the really interesting thing about MongoDB is that it supports actual indexes. So unlike CouchDB, which you have these views that have to get materialized on demand, MongoDB will keep an index up to date for you, right? So you want to query a particular property of that database quickly, and with MongoDB, every time you update that property on an object or you add a new object that has that property, it will update that index for you. So it sort of trades off some write speed for having consistent read performance. And another really cool thing about MongoDB that CouchDB does not have is nested documents. So in CouchDB, it's effectively a sort of key value store. You have a URL to the document and then the document. There's no way to have documents that are interrelated to one another except in your application. But in MongoDB, you can actually have documents that refer to other documents, and the database will maintain that for you. And it just has way more advanced query functionality than CouchDB does right now. And the other interesting sort of database flavor that I've been working a lot with recently are called column databases. Some of this model is implemented by Bigtable and Cassandra, and others such as Hypertable and HBase. The keys to column databases is that sequential reads are awesome. Right? If you don't have to seek around on the disk, it's just way faster. And that if you store a single column together, usually the data is relatively homogeneous, right? And so if you have, say, a gender field, which only has two values, male and female, if you compress a bunch of M's and F's in a row, it's going to compress really well. But if you were to combine that with the gender and the name, then it would not compress nearly as well. And the other cool thing about column databases is because you store each column separately, you only have to do I/O on the columns that you're interested in. So if you have, say, a column database that stores log files, you've got timestamps, you've got user agents, you've got URLs and all those things. And normally if you're doing a query, you only care about one or two of those columns. So in a column database, when you're doing that big sequential scan, you only have to do the I/O for those columns that you're interested in. And one of the column databases out there in the open source world is called MonetDB, which coincidentally has the same home as Python. But it's a research project. Even though it's been around for a couple years, we tried really hard to get it to work. But it crashes a lot and corrupts your data. So if you search for column databases, you will come across MonetDB, but just don't waste your time until somebody proves otherwise that it actually does work. And another system that I've come across, but I haven't played with too much, is called LucidDB. It sounds interesting, but I don't have any experience with it, so I can't speak to how good it is at what it does. It's a hybrid Java and C++ application, and it doesn't support clustering yet, so you only get single node performance. But single node performance of a column database for the kind of workload that a column database needs to do is often way faster than a big cluster of relational machines. And the column database that we actually use is called Vertica. It's unfortunately a commercial column store based on a research project from MIT called CStore. And Vertica, on top of CStore, it adds a bunch of new features, including clustering. But ideally, I would still prefer an open source project, although Vertica does actually work, which is something I couldn't say about MonetDB. And one of the other things that column databases use to make them really fast is something called a bitmap index. And normally, relational databases, they have B-tree indexes. At the ORM talk, he was talking about trees and stuff. But with a column database, normally you're doing a mostly sort of sequential scan all the time. So in order to make that faster, you can basically take your gender column and turn it into one bit per cell value. And you can actually do math on the indexes if you want to find the logical AND of several columns. you can just do an AND of the bitmap indexes, and then you know which rows to actually load from disk. And the same with OR and several other logical operations. And you can compress these for even better performance. Oracle uses a byte-aligned bitmap coding, and there's a really cool open source bitmap index project called FastBit that implements a word-aligned hybrid bitmap coding. It's basically a lot of math, but they do compression, and it works really well. And so what you use bitmap indexes for are big queries. For example, Postgres since 8.1 has used in-memory bitmap indexes to actually do merges of several tables. So when you're doing a big join, if you look at the explain output, sometimes you'll see a bitmap index in there. And that's because you just do a lot less I/O if you're working with 2 bits per row instead of 32 bits or 64 bits or whatever. And it's basically almost a requirement for a column store to implement bitmap indexes. And the other thing that we've been looking a lot at lately, and it's used by Bigtable and Cassandra and some other project, is called a Bloom filter. Bloom filters are really neat. Unlike most data structures that you're familiar with, it's a probabilistic data structure, which means that it's lossy. You lose data. But in exchange for losing data, you can store all this information in constant space. And what Bloom filters give you are false positives at a known error rate. And I won't bore you with all of the math, but a Bloom filter looks something like this, where you basically take several hashes of a value, several different hash algorithms, usually derived from one hash algorithm, and those are the X, Y, and Z for that one value. And the W is the data that you're looking for when it's put through the same hash algorithm. And if all the bits are set for that value, then that means that that value is probably in the Bloom filter. But if you don't find all those bits set, then you know for sure that your Bloom filter has never seen that object. So what you do with that is you can store, say, a Bloom filter for a bunch of nodes. Squid uses this for its cache protocol. And so if you know the Bloom filter for all of your other nodes, you can just do locally the computation to see if the data might be in one of those nodes. And for the nodes that it's definitely not in, you just don't have to talk to. So it saves you a lot of communication. And Bloom filters, you can use them to find stuff, maybe. Another interesting use is that you can use it to approximate a count of something. Like say if you take your web server logs and you want to approximate how many people are going to your site, you can use a Bloom filter over all the unique IPs in your log. Even if you have a terabyte of IPs, you can do this in constant space with a Bloom filter. Although it doesn't allow you to distribute it over a bunch of nodes in an easy way. And there's a bunch of variations on Bloom filters that allow you to do slightly more interesting things. And that's all I had to talk about. And if you want to actually talk about using distributed databases, particularly Cassandra, Jonathan Ellis is doing an open space later today at the Lambert Room. So if anyone has any questions.
You mentioned Hypertable and HBase. Could you fill in some details about those and where they would fit into that ecosystem?
So Hypertable and HBase are basically clones of the Bigtable system. But for my particular use cases, they didn't fall into the interesting bucket because they depend on the whole Hadoop and HDFS infrastructure, and it sort of introduces a fair amount of latency for using it, and that's just not ideal for us to add all that latency in because we do a lot of queries to these systems. But they do fit into the sort of Bigtable model.
So thanks for MochiWeb, by the way, because it made Couch a lot faster. So I had a particular question about the Mongo versus CouchDB thing, and you were talking about the nested documents. And I'm wondering what advantage that has to just nesting different JSON objects inside of a single document in Couch, because since the views are just code, you can kind of infinitely go down and index them either all as the same object, or you can use a sorting algorithm to actually index them as they're nested.
So the use cases I see for that are, say, you have a blog entry and a bunch of comments related to that blog entry. With the Couch model, you basically have to store blog entries and comments as siblings to one another, which when you're creating those views, you have to walk over all of them, even though the comments aren't interesting when you're trying to query the blog entries and vice versa. But in Mongo, you can actually store the comments inside of the blog entry object. And when you update a comment, it doesn't have to rewrite the whole blog entry object.
Okay.
So it gives you better update insert performance, and it can give you better query performance because you don't have to walk.
You have to iterate back over, in the Couch view, right?
Yeah.
Okay. And so the partitioning and sharding is actually being worked on for Couch. But one thing that I wanted to ask is that, so you mentioned that the Mongo's doing the indexes, and Couch isn't doing the indexes, so the writes are actually much, much faster because it doesn't have to incur any of the write costs.
Yes.
Sharding a lot later. Or at least, sorry, you hit the need for sharding a lot later because you don't max out your writes per node very quickly, is what I'd like to say.
Yeah, but when you're generating a view, you can bottleneck on that if you have too many objects.
Well, but that's why it's map reduced and you can distribute it, right?
We only have about 3 minutes.
Sorry.
Hi, I think you've done a good job of presenting an overview of modern data storage systems, but I just found that graph databases were missing. Have you looked at them? So sort of HyperGraphDB or Neo4j, for example?
I haven't run across any use cases personally for graph databases, so I don't have any experience with them.
Okay, so I would just wanted to say to everybody, for a complete view of where data storage is moving, you should probably look at those as well.
Yeah, object databases and graph databases are definitely interesting, but I just haven't had any particular use cases for them in the past couple of years.
Okay, thank you.
So I haven't thought about this question very much, but for relational databases, you have SQLite for the cases where you don't want a network server, you don't want a configuration. Is there anything like that for key value store type?
Yeah, so the Tokyo cabinet, for example, that's a single node system. Tokyo cabinet operates in much the same way as SQLite, and Tokyo Tyrant is basically just a network socket on top of that allows you to have other machines or other processes talking to one store.
Okay, cool. I'll have a look.
Have you ever used Hadoop, or what's your opinion of it?
We've experimented a bit with Hadoop for map-reduced loads, but it had more overhead than just doing it in simpler ways for our workloads.